The first lecture is going to be about introduction to complex survey data, and for that I'm just going to use some of the documentation that I have written over the years. So in general, the outline of this particular document is that at first I will review some of the model based approach, and you are mostly familiar with this model based approach, but I'm going to go into detail about that when I discuss that particular chapter. Then I'm going to introduce what is called a design based approach, which is something new that you are probably going to learn in this course. And then I will introduce you to some of the potential data sources of the complex survey design examples, and some other examples that might be useful to you. And then as a part of that example, I will introduce two different data sources. One is the Canadian Community Health Survey. Particularly I will be focusing on the annual components, but there are many other different optional components that you can also use. Particularly in this lecture, I will focus on how to import those data into your computer, especially in R. So in this particular course, we will be focusing all of our analysis in one particular software. I know many of you come from many different backgrounds, and you are probably familiar with different softwares like SAS, SPSS, Data, R, and all that. But for the management of this course, I had to choose one software, and since R is a free and open source software, that is why I'm choosing R for this particular course. So the another survey data analysis example that I will show is from the US CDC. It's called the National Health and Nutrition Examination Survey, or the NHANES. I will discuss about some of the data and documentation structure for that enhanced data, and then I will also show you how to import that data into R. Let's go to the model based approach chapter, and in this particular chapter I'm not going to focus too much about this particular chapter, because this is basically the review material of some of the methods that you have already seen in your SPPH 400 or SPPH 500, and some of the assumptions that we operate here under are that your data is coming from an infinite population, and that infinite population has or follows a data distribution such as normal distribution, and the data set that you are dealing with is just a sample data set that you are dealing with from the entire population, whereas the entire population is the infinite data that you do not have access to, and the sample is something that you have access to, and that is a part of that entire population. Since this model based approach is operating under the condition that you have a specific distribution, so all of the inferences that you make out of this model based approach is based on how good your assumption is. Say for example, if you are assuming that the original infinite population is being generated from a normal distribution, and if the normality is not a satisfying assumption for the dataset that you are dealing with, then all of the inferences that you are making out of that sample, say for example estimating the odds ratio or the risk ratio or whatever you are estimating, or whether you are estimating the p-value or doing some sort of hypothesis testing, are going to be dependent on whether your data is satisfying the assumption that you made about the data generating condition. So all of these methods that you have dealt with in your SPPH 400 and 500 are based on this model based approach. So here is an example that I have incorporated from a very popular textbook, and in this particular example what they are dealing with is two different samples. So one sample is known as the treatment group, another sample is known as the control group. So basically we are dealing with some plants, and we are essentially giving them some fertilizer in the treatment group, and we are not giving any fertilizer, or we are raising them under standard conditions in the control group. And we are also getting this data from a completely randomized experimental design. That means that who gets to be in the treatment group and who gets to be in the control group are completely randomized. So in this particular situation, the research question is we want to test whether there is any difference in the yield or the weight between the two groups. So we simply weight the plants from the treatment group and the control group, and we take some sort of average, and then try to figure out whether by giving these fertilizers to this treatment group is increasing or decreasing their weights or yield compared to the control group condition or the standard condition that the control group is working under. So in this particular example, we are dealing with a scenario where we have 20 plants in all of these groups. So in the treatment group you have 20 plants, you have in the control group you have 20 plants, and there are two different groups, as I have mentioned earlier. One is the treatment group, that means the treat or j equals 1, and we have the control group where the CTL or the j equals 2. And to denote the yield or the ultimate observation, we have this notation y. So that means that when we have y sub j and k, that means it is the kth observation of the weight in the jth group. So if it is y sub 1 and 1, that means that it is the first observation of weight in the first group. And what is the first group? Our first group is basically the treatment group. Alright, now here comes the assumption under which we are operating. We are assuming that our data is being generated, the infinite population data is being generated from a random variable that follows a normal distribution with specific mean and standard deviation. And we are also operating under the condition that the standard deviations or the variances of both of these treatment group and the control groups are not very different. In other words, it is similar, to the extent that we can simply pull the standard errors and claim that that is the standard error for each of these groups. So the hypothesis that we want to test, remember what was the research question? The research question was that whether there is any difference in yield between the two groups. What are the two groups? The treated group and the treatment group and the control group. So the hypothesis is basically here is the mean of the yield in the treated group and the mean in the yield in the control group are going to be same, equal to some specific mu, and the alternative hypothesis is that they are not the same, right? So let's just take a look at the data. These are some of the data sets that were given in that text, and you have 10 samples in the control group and you have 10 samples in the treatment group. So in this code, what R is doing, R is simply assigning what these numbers represent. So for example, we are saying that these numbers are coming from the control group and we are saying that these numbers are coming from the treatment group when we assign these groups. So we simply aggregate all of these weights from the control group and the treatment group, and we name a variable weight, and we create an entire data frame where we include both of these weights and groups in the data set. So what does that look like? So in a if you look at the entire entry, you will see 10 of these are in the control group and rest of the 10 are in the treated group, and these are the yields that you get. So what is the first thing you should do when you get to see a data? Usually it is a very good idea to do some sort of visualization. So for example, in this case what we are doing is that we are making a box plot, and you can see all of these codes here to create this box plot, and you can see the control condition. Under the control condition the weights are higher, and under the treated conditions the median of the, or the mean of the weights are lower compared to the control conditions. So from here, without making any inference, just from the descriptive numbers, you can see that maybe after giving the fertilizers, in the treatment group the weights are decreasing, right? So obviously we are making some sort of assumptions, and we want to check those assumptions before going into any hypothesis testing. So remember, in the first assumption that we made, the first assumption was that they are coming from a normal distribution, and the second assumption we are making is that the variances are homogeneous or very similar. So to check the first assumption, we simply do a Shapiro-Wilks normality test, and we see that the p-value is much higher. So from this, and also we can do some sort of QQ norm plot to see whether the data that we have are deviating too much from normality or not. So based on this Shapiro-Wilks test, we can say that the data is not following a very different pattern compared to the normally distributed data set. Also, to test the homogeneity, there are a couple of tests of homogeneity. One of the tests that I'm using here is the Bartlett's test, and based on that test I'm getting a p-value that is very high. So from that I can conclude that maybe the homogeneity assumption is not also violated. So from here we have seen that normality assumption is not violated by this test, and homogeneity assumption is also not violated by this test. Alright, so obviously this is a very simplistic problem where you have two samples, and you can simply do a t-test of the weights based on the groups, and based on the p-value of the t-test you can see that the mean values are not very different, and that is why the p-values are very high. So even though we can see that the control conditions weight are higher compared to the treated condition, we cannot necessarily say that they are significantly different. And of course you can do the same test in a slightly different way. You can, instead of checking the or comparing the means, you can simply check the slope of this group in this regression, and say for example here weight is the outcome and group is the independent variable that is explaining your weight. If you set up your regression like that, then eventually what will happen is that you are supposed to get some sort of intercept as well as the slope for the group effect. So for this, treatment is the reference, control is the reference, and you are getting the beta coefficient or the slope coefficient for the treatment group. And you can see there is a beta coefficient. The question is whether this beta coefficient is significant or not. You can simply check the confidence interval, and you can see within this confidence interval the value 0 is included, right? So one of the interpretation that we can probably make from this is that if this slope is not significant, that means what? That means probably the intercept is enough to explain what is happening with the relationship between weight and group, and there is not much significant change based on how group is impacting the weights. And also you can check some regression plots and things like that, and check the assumptions for the residuals, because even for the regressions you are operating under the assumption that the residuals from your regression are following the normality. So you can do some QQ plot or the Shapiro-Wilks test of normality to check whether your regression is following that assumption or not. Alright, so and the third way that you can test this assumption is to work with the analysis of variance, because analysis of variance is basically a generalization of the t-test that you have done earlier, and you can basically check based on this analysis of variance whether there is a difference in the means, right? So if you do the ANOVA test here, even in all of these cases you will see the p-values that you are getting out of these ANOVAs are going to be not significant, and if you do some sort of multiple comparison, which is not necessarily needed for this purpose, but you can if you do that test, you essentially get the very similar results in here. And you can also do some sort of non-parametric version of that ANOVA, which can be done using a Kruskal-Wallis test, and you can also see the p-value is not significant. So I mean, generally speaking, the verdict is, even though based on the point estimates or from the box plots you can see that the control condition, under the control condition, the weight is much higher compared to the treated group, but we cannot confidently conclude that the fertilizer or the nutrition is having a harmful effect for the plant. Notice here that we are simply operating under two variables, right? One variable is the weight variable, one variable is the group variable, and in these two in this experiment there are two conditions. One is the treatment condition and one is the control condition, and we are getting some yield after doing this experiment. So even though we are trying to get the answer whether they are different or not, but we are inherently having this causal question that whether giving fertilizer or nutrition to the plant is helpful or harmful to the plant or not. So this is just the nature how we try to frame our research question. Even though our dataset sometimes do not support the causality aspect of our question, but whenever we are posing a question, generally we try to have a sense of that cause, whether fertilizer or nutrition is causing something, causing your weight to go up and down. But as you know from your previous courses, causation is much harder to establish, and for that just having correlation is not enough. Fortunately, in this particular example, there was a time sequence that you can establish. You already know that there was a randomization, and after randomization 2 groups were formed, and then the yields came after forming those groups. So just based on looking at the data, it was not possible for us to justify whether there was any causation or not, we needed to have the understanding of how the experiment was done, and so we need some subject area knowledge and knowledge about the study design before we can make any kind of inference or interpretation properly.